Ranak everybody, we continue talking about tolerance, accuracy and different element types. And today we compare not only tetra elements but hex element. And yes, I know about presence such type of elements like beam and shell, but we talk here about solid elements and their type. So about different type of tetra elements, about comparing the linear tetra without midsides and nonlinear or quadratic tetra with midsides. We already talked. You can find information here, and we understand that this element for most type of element task are not very accurate. They can be used for some type of task, for example for thermal. They can be used even for stress calculation, but for explicit, for nonlinear task, and you need to create a mesh which will have good stress and stiffness distribution with this linear tetra, and sometimes it's even recommended to use this linear tetra instead of nonlinear tetra. But in 80% of task, and it's in most cases linear task with linear material behavior, this type of element, linear tetra, will provide very non-accurate results, and you need very fine mesh to obtain good solution. But we also have hex element and wedge and prism. We don't talk about wedge and prism today. We don't talk about pyramid. We talk about hex element, because in general, if we create or simply tetra element or mostly this element, this type of elements or hex or tetra will be will have maximum percentage. So we talk about only these two type of elements, about hex and about tetra. And this is a linear hexa, and we need to understand, does it the same situation like this linear tetra, so it's very bad, or maybe it's something different? As an accurate and tolerant solution, we will use a beam which meshed with hex mesh, and this mesh not only have 10 elements per side and 100 elements per length, but also it's quadratic element with mid-side. So these bars are 100 elements, 100 millimeters per length and 10 millimeters per side. For beams obtained by copying, they have the same structural steel material, they have the same volume, the same sides, they have the similar boundary condition, so it's fully fixed on one face, and the force which applied to opposite face. This force applied in one step for all these faces, and in reason that we have 4 same faces and we apply in 4000 newtons, we obtain 1000 of newtons per every face here. So we have the same cantilever beam with the same type of fixation and same loads. But if we take a look into result, we will see some difference. And if we choose this corner, we can see that we, for this 3 type, have almost the same result. Here, difference in the third sign after the point, and here the difference in the second digit after the point. So it's around 3%, and it's around less than 1% of difference. So both of them, all three of them, have the same accuracy for this mesh. And this one, the last, have in 5 times less displacement than the previous 3. That's why it's very not accurate, and that's why we need much more fine mesh for obtaining a good result. But the problem not only in displacement distribution, not only in stiffness distributions, the problem are in stress distribution. And if we take a look here, we can see that we have two almost the same picture. Yep, it's more coarse, it's more wavy, but we can see that the character of stress distribution for this and this place almost the same. We have some difference here on the top and bottom faces, but in general it looks the same. So this one have the same colors but doesn't have natural plane with 0 stress, so it's tricky solution. And this one have something very small in stresses, and it can be simple to understand how the stress distribution look like in this scale. So for this time we use the scale only for this beam, and we can see that stress distribution are very different from the accurate one and very, very tricky. It have very strange line, it have one corner and so on. So it's came with this mesh and it's very non-accurate. And the reason of which it's non-accurate, it's a non-averaged stress distribution. Because when we talk about this one, or even this one, it's average. It's average stress distribution. What does it mean? It means that we take stress from all elements around the node and obtain mean value with different algorithms for these nodes. And then we draw this picture which change linear stress from one point to another. So it look more affordable and more accurate. And these variants show that our mesh are not so accurate and show that our results are not the same from the different elements here. And even for very good and fine mesh, we can find the same situation. So this is an averaged value, and we can see that this element has the linear stress distribution. It changed from one node to another node inside of one element, and we can find it's also here. But in some case, it's not changed in those direction, in the direction of height, in the direction of folding and bending. So this one have and this one doesn't have, and it's can be tricky to understand what is going on here. So we take a look here. And this is an averaged von Mises stress for our beam with linear tetra element. And we can see that there are no linear stress distribution between the nodes, we can see the constant color for any element. We need to understand that mesh here look very different and came with very strange way. That's why it look so different in colors. But we can see that for every element we have only the one color, only the constant stress distribution. And that's why we don't use this linear tetra, especially with coarse mesh, for the linear material behavior. For nonlinear material behavior, those type of stress distribution sometimes can simplify convergence and simplify work with those type of tasks, so it's different. Okay, let's talk about not von Mises stress, but about component stress, because they can show to us does we have problem with stress distribution or does it correct. And if we take a look into stress distribution on x and y direction, this and this, we can understand that it's not the real one which we need. Let's say 1 megapascal and minus 1 megapascal. And we can see that almost everywhere outside of places of applying forces and applying fixation, we have zero stress distribution in all directions. And in reason of mesh, in reason of boundary condition, we have here not zero values, and it's look like this one, but it's not the stress we need, and we need only this one, only around z axis v or z. So it's stress which show to us where construction tensile and where construction is compressed, and we obtain it with the sign of the stress. Minus it means compressed, and plus it means tensile. Here in your software it can be different, but in most cases it looks like this one: compression minus, tensile plus. And we can see that only this one doesn't have change their value through the thickness. We can see changing this value inside of thickness for quadratic tetra element, and we can see it for linear hex element. But maybe it's only, as we say, linearization of mean value because it's averaged. So let's look into unaveraged result. And we can see that this object have constant stress, and these have linear stress distribution between different nodes. And every element have their own stress distribution, but it's linear from point to point, from node to node. And the same picture we can see here. So it's linear from one node to another, from one node to another, from one node to another. And if we do something like this one, so everything is red, it's tensile, everything is blue, it's compressed, we can see how it changed, and we can see that here it's very non-accurate. Here we have very smooth result, only here in reason of forces we have some problem. And here we have the same situation, it's almost smooth, and here we have some additional problem. We can see it here also. So we can see that this hex element with linear behavior, with 8 nodes per element, are almost the same by quality and accuracy as this one, as nonlinear tetra. But this mesh have the nodes like this one, twice less than this one. Let's check. Linear tetra element has 46 nodes, 72 elements. Quadratic has 60 elements and 200, almost 200 of nodes. It's 2.5. And this one have 44 nodes. This 46. And only 10 elements, not 72. So this mesh will have the same number of nodes as this one, and the matrix will solve and needs the same resources to calculate. But these elements have more difficult description than this one. It's more like for this one. So the total time of calculation will be for these two beams are almost the same. It's no matter that these have 7 times more elements than this one. But accuracy, as you see, are very slightly different. And we need to explain why we doesn't have here the same beam, but with additional mid-side nodes. So it will be quadratic hex element. But I will not do this in this video. You can write your presumption in the comment, or maybe you know answer why we don't use here a quadratic nonlinear hex element with 20 nodes per side. I hope this video will be helpful to you. Bye.